Today on the AI Applied podcast, we have a very special guest that we have been trying to wrangle for months now. So grateful that he's going to give us some of his time to talk about the massive AI landscape, Kai Beckman. And I'm going to just make sure I get this title right, Kai. But Kai is the CEO of the electronics business of, stay with me, folks, it's Merck KGaA at Darmstadt, Germany. But in the U.S. here, it is known as EMD Electronics. But a lot of those names you'll recognize. And one of the reasons that we wanted to invite Kai on is because this is a extremely old institution, but it's really an institution that helps run a ton of what's happening in the AI world, kind of behind the scenes. And Jade and I are usually on the cutting edge of talking about, hey, this is all like the sort of the whiz bang tech that's in the news right now. But really, one of the things we're really interested in just hearing and learning more about is that what does this supply chain look going all the way back? What are the huge issues? What are the issues around chips and everything else? And Kai Beckman, I'm hoping will share a lot. Kai, thank you for joining.
Connor, thanks for having me.
Jaden, you wanna kick us off? I have a ton of things, but I don't want to monopolize the time. If you want to sort of if you want to kick off the conversation.
Yeah. Okay, first off, thanks so much for coming on, Kai. This is super awesome. We're excited to have you. The first thing I would love to pick your brain about is I'm wondering if you can talk a little bit about, how do you actually create more efficient chips? This is something that you guys are doing. It's obviously a big challenge in a lot of different ways. When you're talking about higher performance or more sustainable, this is something that everyone is focusing on. So I guess I would love to hear from you a little bit about your approach and how you guys are accomplishing this.
Jaden, thanks a lot for the question, because it's very important maybe to start with why are materials so important for making chips work as they work? Because traditionally, the semiconductor industry was driven by lithography. You want to get smaller structures and even smaller structures, and kind of the wavelengths of light was the limiting factor. This is what is behind extreme ultraviolet, EUV. All these areas are probably known to many people. Meanwhile, at the same kind of extent of importance, the is developing new materials that make these incredibly small structures work, and that's more than just supplying kind of layers on top of a silicon wafer. It is about how can I make structures in the nanometer scale able to conduct electricity in the way it should. So, and this is it's a big deal because these structures get so small. We're talking about a few atom layers in these structures that will create limitations from a physical standpoint on, for example, conducting electricity. And these materials that make that happen, they come in many instances from our company. Our company covers a full spectrum in all different processes of making a chip, which is up to 1,000 or more than 1,000 steps to making that chip work. And this is what we contribute. For example, materials in lithography, materials in patterning, materials in deposition. We're creating these ultra fine structures, planarization to kind of planarize the chip after these structures are being made, cleans and what have you. So this is what kind of chemistry can do to improve the performance of these chips.
Yeah, it's amazing to kind of get into that part of the conversation for me anyway, because I know sort of, again, when we're talking with folks about this, people are coming on and they're even, sometimes they're at the stage of just trying to figure out how to use generative AI, for example. But I know that they also see in the headlines these notions of, is there a chip shortage or is there a material shortage? And when you hear, the huge kind of like rock stars in this world, like the Sam Altmans and people like that talking about it, they're talking about these colossal investments in just sheer compute. And so you're associated with this company, sort of going back, I think over like 300 years or something, but you are, you're sort of really integrated into the global supply chain around all this stuff. from your standpoint, just when you're kind of like reading these headlines and everything, how does it look to you? I mean, is it for you? Is it sort of like a raw materials thing? Is it just like how fast can you create these things? Like, what is it when people are saying like, oh, we're getting held back from GPT-5 because there's not enough compute? How does where do you figure into all that, and how do you see all that?
Of course, what drives me and our team over here, what drives us is, of course, helping to improve the performance of these chips, which is an essential component of making AI happen the way we want to have it. And for example, if you go back into how did the training for GPT-4 happen? I think that at least literature tells it's 5 to 6 months, 10,000 V100 cores, and it's the amount of energy of 7,200 megawatts hours of energy. That's quite a lot. So, there's 10,000 GPUs running 150 days on full speed. That's what, and this is the limitation still, energy and time. And so the next generation has to be even faster and even more energy efficient. I think we have seen a few days ago NVIDIA announcing the Rubin platform, which is even more powerful. It's required. If you want to train more complicated models with trillions of parameters, we have to go the next step into miniaturization and integration of these devices. So this is the primary driver of our performance here in our company, is the ambition to make the next generation of semiconductor devices possible. Second is, and you were referring to shortages and supply, the whole thing, of course, is based on the assumption we need the right material at the right time, at the right quality, in the right quantity, at the right place, which is complicated. This is more complicated than it seems because geopolitics become more complicated. Logistic routes are being more impacted by complexity. We had COVID for a few years, and so to ensure that the fabs of our customers are not running dry on materials is quite a big deal. So that's the second dimension, is kind of supply chain, to have the right materials at the right place. And this is about how can we scale production, because demand is increasing quite rapidly. The industry is up to being a $1 trillion industry by the end of the decade. This is the semiconductor industry's ambition, and that means from if you take this year's number, it's about doubling in a few years. And what happened in the past 60 to 70 years is now happening in the next 6 years again, 500 billion. And the third element is quality, and quality is paramount in this industry. We're talking about structures of 2 nanometers, 3 nanometers. That's the kind of the current structure size. And just to be clear, what does 2 nanometer mean? This is 20 angstroms. This is we're talking here about angstrom. We're at atom scale. So the silicon atom is more than 1 angstrom. It means we are talking about less than 20 silicon atoms in these structure sizes. So that's a pretty ambitious target to make that work. And then we talk about a chip, if you're a bit more generous. So the NVIDIA Blackwell B200 is not really a chip, it's a system at the end, it's glued together. But we're talking about 208 billion transistors. 208 billion transistors. And now comes the fun part, they all have to work. and they are all on nanometer scale, have to work. So, and quality is paramount. So we talk about parts per trillion, and in terms of quality expectations, parts per trillion, to give you an image, is it's the size of a football on Antarctica.
Oh my gosh.
You mean, at the end, the second football on the Antarctica would already kind of be above the expectation of our customers.
Really,
so gives you an idea about the complexity of the value chain in semiconductors. And now coming a bit to chemistry. I think we all have in mind from our days in school the periodic table of elements. Probably have seen it before, and you have the image in mind. Pat Gelsinger was well known in this industry, and that doesn't need to be explained. He had put a post on X just 2.5 weeks ago, where he said we are going to stop innovating semiconductors until we have exploited the full periodic table of elements. The meaning, and this is not really kind of far from today, because currently we're using 50% of the elements of the periodic table of elements for semiconductor manufacturing. 50%. Can you imagine that? That's quite a bit. So because if you probably would do a survey on the streets, people would say, okay, it's silicon, and silicon is one. Right. It's 50% of the periodic table is being used in production of semiconductors.
So it's so complex. Kai, what I'd love to ask you about, so you have 50% of the periodic table of elements built into these. There's these supply chain issues. There's energy constraints. What I'd love to hear from you is, what do you think the bottlenecks are as we look at like truly scaling up our production of more chips? And if we really want to train, you see things right around the corner like OpenAI's Sora model, which is going to be video. If everyone is going to be doing video models in the future, and this is incredible amounts of compute that are going to be needed, what do you think the bottlenecks are? What are you concerned about in this area as far as the things we need to be concerned about? Even NVIDIA, is this going to be supply chain? Is it going to be elements? What are we concerned about here?
I think the real economic constraint will be energy going forward. If you scale the current consumption, it is next to unaffordable to kind of scale the consumption based on today's technology. This is energy. I think in the past, probably time would have been the issue, because if it takes years to train a model, then the economic value probably is low. And time, of course, can be tackled by compute power. But energy, if energy would scale linear, and given, of course, all our ambitions in carbon neutrality, this energy will be the bottleneck. This is why innovating in energy efficiency, which of course goes together with speed and all these different factors, is absolutely essential.
Yeah, of course, right? And I mean, it seems so obvious when you say it, but it's again, so many of our, not just our listeners, but just the headlines that we read, it's all the very, very end user. You know what I mean? It's all like, hey, this, Anthropic's model was slower today. It's very much that. And the reason that we wanted to sort of, pick your brain on this as well is that when we think about those giant challenges like the energy and like 50% of the periodic table and just these tiny numbers and things like that, where, like, who do you partner with on all this? Because like you can't solve everything, and it feels like your organization, again, has been around for so long and is responsible for so much of this stuff going in. I just spent the last few days at SAP Sapphire, and just like hearing Jensen Huang talk about the miles of cables and everything else, sort of like what you're talking about. And these things are, at least in part, coming from you. So you can't do it all. So when you're kind of like, I don't want to kind of put nightmares in your brain here, Kai, but like, what's keeping you up at night? I mean, is it sort of like this energy thing? Do you have visibility into the other organizations who are really focused on energy and sort of like how we're going to use this more efficiently? Or is that something that you all have, and I don't know, but like a lab working on or something like that? Or how do you, when you think about how we're going to solve those problems, where do you think those solutions end up coming from?
This is just to get it right, Connor. It's not a one-dimensional optimization where energy is the only variable. At the end, I think I said it all starts with, can we produce these materials at the right quality? Because that's right. Absolutely essential. And quality. And you were referring to the history of our company. 356 years is quite a bit, of course. 356 years, I must admit, are not in semiconductors, obviously. So it started as a pharmacy, but one of the leaders back in the 19th century, he made a quality promise already, kind of an unconstrained quality promise. That was the first one in this industry. So quality is in our genes, in our company. Quality to make the the best quality possible is the basis of how we work in our company. So EMD Electronics stands for purity of formulations we produce. That's the starting point. And then comes, of course, at the end, functionality, because these products have to do what they are supposed to do. And that's the performance that these products have to have on a device. Who do we partner with? Of course, with the chip makers, with the foundries, with the IDMs, so companies who then optimize their products based on the input we are able to provide. We are working together with the tool companies, of course, the big tool companies who then qualify processes based on their tools and our materials. That is the way done together with tool companies. And of course, we do work together with academia and research institutes. IMEC here in Leuven, near Brussels in Belgium, a very important institute that helps us then to like work 2 nodes ahead of time in optimizing it. So there's a big ecosystem. It's not a kind of a thing done single-handedly by us. Clearly, this is a collaboration thing. But it's more, the collaboration in this industry is getting more important as we go forward. It used to be more bilateral, and it's more a kind of a bigger collaboration in the industry to make these new devices happen. And then, so once we have established new technologies, they are qualified by our customers, then we can produce it at scale and offer then opportunities to companies like NVIDIA that we were referring to, like AMD or others who are then fabless companies who then take kind of the benefits of the technology development of the value chain kind of below them. That is the way how this market works, and it's pretty exciting because you see these things like, I don't know, 2 generations, 3 generations ahead of time. That is pretty exciting business to work in.
100%. I think there's so much innovation. This is why everyone's so interested in this topic right now. And obviously, your company gets a lot of the spotlight because you're behind the scenes, kind of making this happen. Something I'd love to pick your brain on is, you talk about seeing things a couple generations ahead of time. You kind of are. It's like you don't have a crystal ball, but it feels like because you're making the underlying hardware or the chips that are going to be able to run a lot of this stuff, you get a sense of things that will be possible in the future. I'd love to hear your thoughts on what are some predictions, or maybe not even predictions, but what are some things that you think are really exciting that you're looking forward to that are coming down the pipe in the future? Maybe not capabilities we have today, but you see them on the horizon based off of kind of what's going on in the space you guys are building in.
Yeah, so I'm of course supercharged by kind of a conference I was participating in. I was allowed to kind of give a keynote there, the so-called ITF World from IMEC in Belgium, and this is always like supercharging you with what's next. And so if I would summarize that, and I hope I do justice to all the great presentations over there, is because this industry is defined on what's called shrink. So that's the essence of that industry, making things smaller. This is the basis of Moore's law, is to make structures smaller. Since it's kind of getting more expensive and a bit more complicated to get always smaller, there is the next level of development is called heterogeneous integration. And this is what you see in the end products of NVIDIA. These are not single chips, it is systems and of chiplets glued together in one big device, and it's amazing what's possible on those devices. It's called heterogeneous integration, an amazing step forward. This is already happens for a couple of years, and the next frontier here goes in directions of using light as a kind of means of connectivity instead of electrons, because light have the advantage you don't create as much heat. So it's more energy efficient. So photonics, very important topic. And if you think further, we may be reaching the limits of current architectures. So the current architectures are still built on the von Neumann principle, with kind of a memory CPU bottleneck, and so kind of post von Neumann architecture devices such as neuromorphic devices. Even you could include quantum computing in that spectrum. That's the next frontier, and that's not just crystal ball. Things are happening, and then of course for a company with such a rich heritage of chemistry, physics, biology, and different areas. Of course, the big thing in the future is biology. So there is it's called bioconvergence. So the overlap between electronics and biology, and the potential synergies going forward. This is mind-boggling. It's hard to even imagine what's possible there. So to imagine that the entire storage production of the world in digital storage would fit into a shoebox of DNA. And this is even an overstatement, shoebox. Probably it's half a shoebox. But so, but it's of course, it's far down the road. So there's a lot to come from where we are today. And if you try to imagine what happened in the last 10 years, and typically the next 10 years, innovation will be faster than what happened in the past 10 years. Now try to extrapolate where we stand. Because most people try to do it linear. Say, okay, last 10 years, next 10 years is linear. It was never correct that it was linear. It typically is exponential.
This is, Kai, I could spend an hour just hearing about your thoughts on the future. That is actually unbelievably mind-blowing to me. So I want to stay there for a second and completely agree on the linear, and just watching how Moore's law has seemed to sort of go out the window a little bit. And also, I mean, I'm assuming that it must be that that even your progressions in AI are then helping. I mean, I'm guessing sort of like there's this great virtuous cycle of you creating materials, and then other people processing it, and then those probably materials are kind of like, or rather those products are feeding back into your system to actually help your system, which is really amazing. Just to sort of dive in there, just because when I hear how quantum computing works, and then the biology, and then light as a form of almost like a transistor. So internally, give us a sense internally, like you have this, an organization, obviously a lot of labs and everything else. Are these things kind of done in silos for you, these different kinds of technology? I mean, when you're talking about, and I know you're not there yet or anything like that, but just sort of like when you think about, kind of projecting out the future, you're talking about bio, and you're talking about light, and you're talking about quantum, everything else. How does that integrate for people who know nothing about this? How does that all fit together? Are they in completely separate labs? People have been working on these issues for 10 years, and then all of a sudden they find a practical application that they can start integrating? Or is it sort of that it's the same kind of people working on it? I'm so ignorant on that topic.
Yeah, that's a great point. And because how innovation is being done in enterprises has changed over time quite a bit. Historically, the picture that you have just painted, labs doing things a bit in a silo, and eventually come up with nice inventions. That was a valid picture maybe 20, 30 years ago. It has changed massively, and last 10 years you see more integration of that. So for example, you've got technology offices that link between these different capabilities, that bring people together, because it could well be that one technology started in one part of the organization may converge with another technology in a different part, and or the chemist understanding a certain molecule that is needed in an area is working elsewhere and need to be looped in. So the kind of a synergistic way of innovation management is absolutely essential, and to bring people together to come up with these ideas. And it's not only within one company, it is more and more within an ecosystem. So talking to people of other companies, of in academia. So it's exciting to see what's possible if 1 + 1 is greater than 2. So and that's the model I would see behind that. And just to get one point right, I'm not amongst those people who declare Moore's law being over. Clearly not. Gordon Moore, and he may rest in peace, he is a genius. He was a genius. I think that the means to accomplish Moore's law change.
Right.
He didn't say that it is only shrink. I think his message was there is kind of an exponential improvement curve, and this exponential curve will be done by even kind of more innovative means. That's a different story. So I did my master's thesis in semiconductor technology in 1989, long time ago. There were many people around in 1989 who said Moore's law is over.
Right.
Many people.
Right.
This is 35 years back in time, and I think we were smiling by remembering. Could it be over in 90? No, not at all. We are, I don't know, X orders of magnitude further than 1989. There are still people who say Moore's law is over. So that's why we call it a bit jokingly in the organization. There's a derived Moore's law that the number of people declaring Moore's law being over doubles every 2 years.
I love your big vocal defense of Moore, by the way. This is great. We walked into, I feel like I walked into a guy who's done his master's in this. So I'm going to take your soundbite and sound so smart going forward. Aiden.
Yeah. Okay. So I think this is really interesting. I love your kind of take on of course Moore's law, because I've definitely heard the argument as well. They're like, well, silicon is reaching its limits and the atoms are getting messed up when we keep making everything smaller, and but like I 100% agree. Like we find new ways. It doesn't mean that, it was on one specific platform or architecture. We find new ways. I swear I just saw like a company in, I believe, Europe that's like using human brain cells and like brain chips on them, and they're like 1,000 times more efficient. Like we are coming up with incredible innovation. Something I'd love to ask you about is, of course, this is one thing that I think sometimes people get wrong. What's maybe another common misconception that people get wrong about the industry, or maybe what you guys are working on? A misconception you feel like you could clear up or set people straight on.
Yeah, there is the increasing visibility of that industry, which of course is for a person who really loves that industry as much as I do. The increasing visibility, first of all, a good thing, because when I talk to people, in '89 when I said I'm working on semiconductors, what the hell is that? Was probably the most frequent response. And meanwhile, if you talk about semiconductors, everyone at every dinner table would expect to have an opinion on that topic. It has changed massively, perception of that in the industry. What is a wrong perception? There is one wrong perception that you can find sometimes in discussions with governments is there is it's a semiconductor seems to look like a commodity. So it can be replaced by simply another semiconductor, and that's nonsense. Of course, there is no such thing. Maybe in memory you find some commoditized versions where you could buy it from different companies and they would do the same job. But basically, semiconductors are so specialized devices that have a very special functionality, and by no means can be easily replaced by simply another one which is identical. And so that is maybe one wrong perception. The other one wrong perception is like semiconductor is silicon. That's it. I try to get across that semiconductor is silicon plus so many additional elements of the periodic table, which create the complexity that you have on a chip. Yeah, so it's far from being just silicon, and that's maybe the second one. Yeah, and if you go one step further, the other kind of wrong perception of semiconductor is, and this is more kind of going deeper in technology. It is just about you got a wafer, and then it's a bit of lithography, and then it's done. That's how it's made. This is already the more sophisticated way to look at it. And I think my message was it is kind of an integration of 1,000 and more process steps to make a chip happen, which at the end, I don't know whether this is known, takes more than 3 months to make one chip. So it's not a factory like you put a silicon wafer in and at the evening you got a chip done on the other side. It is a 3 months process, at least, would be more than that. And it shows the complexity of all this kind of the chemistry interacting, the lithography steps, enormous quality expectations. And so if we then hold it in our hands to do all this stuff, if you hold cell phone, which has probably 16 billion transistors on its CPU, and with all the smart technologies, nanometer scale structures, and what it does at the end, it's playing a cat video. That is what it's all good for. That's the journey of a semiconductor. So that's the way where I would like to help to understand what amazing technology are we able to develop jointly in this industry, and what's possible at the end to be done with it.
I think this is such an important point that you brought up that a lot of people don't think about. And you're like, there's not a factory where you stick it in and it pops out. Like, these things could take 3 months. I think there's this kind of misconception that, oh my gosh, we have all of this new AI technology that's coming out. We need more compute for it. We need more chips. We need more of this and that. Let's just like spin it up quick. And these things take a very long time. You have companies like Google and Meta who are talking about building their own chips and things. And people are like, oh, this is going to solve our chip shortage. And in reality, these things will take years to build the facilities. And there's just so much that goes into them. So when you have companies like NVIDIA or yourself that already has been building up this manufacturing, I mean, you guys are over 350 years old as a company. And I'm sure, not all of that maybe has been in making the chips. But when you have kind of this really rich history and there's this huge pivotal moment, you guys are perfectly positioned to really help supply what is needed today to make AI. So I think that's a really exciting place to be, and definitely something not everyone is aware of, just that the process and how long that supply chain really takes to create some of these chips.
Yeah, I just want to just sort of say that it took us a while to get you on, only because you're so busy, but on behalf of our planet, just get some rest, because this is huge. I mean, it's just thank you so much for joining us, for pulling back the curtain, because again, so many of us are just on the end user side saying, where's our stuff? And you guys are clearly working very hard. It was super exciting to hear how all this is made, and all the exceptionally difficult work that goes into it. So congratulations to you. The team, thank you for joining us. I'll let Jaden see us out, but Kai, I just wanted to say thank you so much.
Yeah, from my end, thanks so much for coming on. And any last words or any last pieces of advice maybe that you could give to people looking at this space, and any last wisdom you can impart on people?
Conrad, Jaden, first of all, thanks for having me in this call. It was really exciting, and to have that conversation. And I'd like to close with, if you want to kind of feel the excitement, you simply got to talk to any one of my 8,000 team members at EMD Electronics, or in a larger scale, the company is more than 60,000 people. You feel the energy. If you go to a lab and people tell you what's possible, what could be accomplished as a next step, that, of course, is keeping me positively awake at night, because it's exciting about it. But it's a candy store thing in one way or another. And I think this is that is in this industry is if I talk to our customers, we feel the same energy. So of course, I do have the pleasure and the privilege sometimes to talk to these phenomenal leaders in the industry. We named a few of them, and I don't want to be incomplete in my list, but we talked about Pat Gelsinger, or we talked about Jensen Huang, and we could kind of look in Zhou as well, and others. And I had the enormous opportunity in my business to talk to these people. And these people, they live for driving that industry to greater heights. And this is something which I find extremely exciting. They do it because they really enjoy it. They really feel that fun to kind of accomplish the next step of evolution in technology, and then we can great things with AI. What's possible with those tools at the end is absolutely exciting. And that's maybe one thing I would like to conclude. The other one is it's always important to understand kind of the full picture, who is able to contribute, and even companies with a 356 years history and a family owned, which sounds a bit in this industry traditional, but Merck KGaA in Darmstadt, Germany, is a company that is able to kind of innovate itself, to renew itself over time, and adjust to what's needed in the world. I find that really exciting. This is what drives me, what makes me really happy about what we can contribute.
So amazing. Kai, thank you again so much for coming on the show today. To the listener, thank you so much for tuning in to the AI Applied podcast. If you haven't already, make sure to go find Kai on LinkedIn and check out what they're building, some incredible things. We'll leave links in the show notes to their website. And thank you so much for tuning in. Make sure to rate us wherever you get your podcasts, and we hope that you all have an amazing rest of your day.